talked about cross-Claisen reactions and cross-Dalibol. And we have these two examples. So both of these give rise to single products. Now, when we talk about cross-Claisens, cross-Dalibols, and whatnot, the only ones we're going to be interested in are the ones that give rise to one product. Reactions that give rise to complicated mixtures of products we really don't care about because they're not practical. So now the question is, how do we tell which ones are going to be useful and practical and which ones will not? Well, the first one kind of easy because look, you have a ketone, you have an ester, but the ester can't enolize, so there's only one nucleophilic partner. So the only nucleophile present is going to be the ketone enolate. Now you can say that, well, okay, but I have ketone enolate, I have ketone, and those two come together and go an alkyl. The answer to that is, well, yes, they can, but the problem is that the cyclohexanone plus cyclohexanone base catalyzed alcohol favors starting material. So even if you do get that first carbon-carbon bond forming process to take place, it's reversible, and then once you get to here, the process is irreversible. Why is this product represent sort of an irreversible endpoint? The reason is because that proton is very acidic, and once that proton is removed, it drives the equilibrium, as we've seen for the other Claisen. So this is an example of a cross-Claisen reaction between ketone and ester that is very useful because it gives a single product for the reason shown. Now, that's not the only one. The other example that we gave last time was acetophenone and ethyl acetate. And so you can say that, well, acetophenone under these conditions can react with acetophenone. Yes, but the equilibrium will favor acetophenone. You can think of ethyl acetate being enolizable, so it can do the regular symmetrical Claisen. But there's a huge difference in pKa between the ketone and the ester. And so because of this large difference between the acidity of this proton and this one, the alpha proton, you get this enolate. This acts only as the electrophile. And then to make sure that this happens, you can also use an excess, and so that's why you end up with a single product. So as long as you remember the mechanisms, you can puzzle out which products excuse me, are going to be formed exclusively. And so this is just the the verbiage going through what I just said moments ago. So cyclohexanone surely can undergo base catalyzed alcohol with itself, but that equilibrium favors the ketone. And then in the second case, that rather huge difference in pKa between ketone and ester ensures that the ketone is going to be the exclusive nucleophile and that the ester will be the electrophile. Okay, so now let's see if we understood any of this. So I have a 1,3-dicarbonyl compound, that's ketoester, and then the question is, well, what's the right way to prepare this? And I've shown two disconnections. I've shown a red disconnection and a green disconnection. So both of these reactions, both the reaction of this enolate and ethyl carbonate, or this enolate and the ethyl ester of phenylacetic acid, both of these will give rise to the same product. But one of these methods is going to give an exclusive product. The other one's likely to give a bit of a mess. So you'll get the right product, but you can get it along with a lot of other things. So which one is the right one? Red or green? Water. Okay, so you need to think about that, figure it out. It's not going to be that hard. So one of them works, one of them doesn't, and you need to figure out why. If you go back to what I just said about those two the examples, it will become clear. Okay, so we talked about the fact that when we talk about soaps and whatnot, we talk about stearic acid being a C18 compound, and I said that, palmitic acid is, I think, C16 and so on. And I said that all these fatty acids, these naturally occurring ones, typically have an even number of carbon atoms. And that points to a iterative process for their biosynthesis. In other words, if you have an iterative process in which you add 2 carbon atoms at a time, then, of course, the final product is going to have an even number of carbon atoms. So let's take a look. This is kind of the abbreviated version of what's in your book. So CoA, C-O-A, this is coenzyme A. It's a very large structure that is, for our discussion right now, not relevant. Notice, however, that this is a thioester. It's not an ester. That's a sulfur atom. And thioesters are more reactive for acyl transfer than esters. Now, they're not like acid chlorides, of course, but they are better, more reactive than normal esters. The reason is because the sulfur is more electronegative than oxygen, and so it can act as a better leaving group than an alkoxide. So a thioalkoxide, S minus is a weaker base than O minus. This is a better leaving group. And so this is a good reagent for transferring an acyl group to a nucleotide. Now, I'm not going to describe how you end up getting the thioester enolate, but that's done enzymatically, and it traps, that enolate traps CO2 to give you this malonyl coenzyme A. Now, why malonyl? Well, because remember, the names of the dicarboxylic acids. The first one was oxalic acid, malonic acid, and so on. This has got 3 carbon atoms, so this is malonic acid monothioester. So malonyl-CoA is the stuff here. Now, what you've done in that first step is you've converted an ester to a diester. Now, think of this as being an ester. So in the process, what has happened to the acidity of this position? These protons are much less acidic here, much more acidic there, because here they're acidified by the presence of 2 carbonyls. So that initial addition of CO2 does a couple of things for you. It makes it easier to deprotonate here, but as you'll see, it also makes it easier to reform that enolate. So this S-CoA, this whole group gets transferred to a protein that's called acyl carrier protein, ACP. And so this CoA transfers the thioester to acyl carrier protein. So acyl carrier protein is a very large molecule, but this is the business end. And on the same acyl carrier protein, this is the same protein, you also have some of the acetyl compound, the thioacetate. And so these are held in close proximity. Now, one of the things that enzymes do is that they catalyze reactions by holding the reagents close to each other. So they act on the delta S term of the activation energy. So in other words, because the 2 reacting pieces can't get very far away from each other, the probability of them reacting together goes up, and therefore the rate goes up. Now, I've summarized kind of 2 steps here. You have to think of CO2 being eliminated from this malonyl, thiomalonyl ester. That's going to give you an enolate, and then that enolate is nucleophilic and adds and transfers the acetyl group, forming this red bond. So the loss of CO2 ensures that the reaction proceeds to completion, right? Because you end up losing CO2. Once you lose CO2, you have a reactive enolate. The reactive enolate is formed in close proximity to an electrophile. That's the piece on the left. And so they react. And at this point, what you've done is you've extended the chain by 2 carbon atoms. So you started out with 2 carbon atoms here, these 2. This one's lost. And then you've added another 2 there. So now we've gone from 2 carbon atoms, not counting this one because that's going to be lost as CO2, to 1, 2, 3, 4. And now you can see that this process is going to be, in one sense, repeatable because of what I'm going to show next. And so the next time you repeat it, we add another 2 carbon atoms, and so on and so forth. And that's why you end up with an even number. Now, the loss of CO2 is a very clever way for nature to get an enolate, because, of course, there's no possibility of using, under physiological conditions, a very strong base. And so that loss of CO2 generates a reactive enolate, reactive species, in close proximity always with the electrophile, and that's what drives the process. Now, once you've got this is still on acyl carrier protein. A series of steps take place. You end up reducing the ketone to the alcohol. Now, this is a beta hydroxy thioester. Loss of hydroxide can take place to get the alpha beta unsaturated. That gets reduced in another step. And now at this point, you've got a 4-carbon fatty acid, that's butyric acid. And then you can that can enter another catalytic cycle, just as you saw before, to introduce another 2 carbon atoms and so on. And so in each cycle, you introduce 2 carbons. Now, it's a number of steps, isn't it? Because after you form the carbon-carbon bond, you need to reduce, eliminate, reduce. But all of this happens iteratively, and you end up, in each case, extending the chain by 2 methylene units. It turns out that this same biosynthetic machinery is used for not just this chemistry, but also for algal chemistry. And so this the same enzyme, the same acyl carrier protein can be purposed to make other kinds of natural products, in addition to fatty acids. But in all cases, you end up adding an even number of carbon atoms when you make the fatty acids. So this is useful. This is a good starting piece for biosynthesis of other types of molecules. So the Claisen condensation is used biosynthetically to form fats. Okay, so now let's take a look at melanate. Now that we have this as an introduction, let's take a look at malonic ester and how we can use it not biosynthetically but in the lab. So let me just kind of go through something with you. So if I have 2 carbonyls in the same molecule, right, and I'm not interested in what this is, then as I indicated, this methylene group becomes a lot more acidic than it would be in the absence of one of these carbonyls. So I've acidified this by an awful lot, over 1 million times, meaning that I can remove that proton rather easily to form a stable enolate. And so deprotonation of a dicarbonyl compound to give you that enolate turns out to be an easy process. And so once formed, that enolate, and you can form it quantitatively, that is a good nucleophile which can react with alkylating agents to form carbon-carbon bonds. And in the case of melanate, that turns out to be useful because of the following. So this is something called malonic ester synthesis, and you don't need to remember the name, but it's easy to understand. You have K here of 13. So you pull this proton off, form the enolate the way I showed, and then you allow that to react with an alkyl halide, any old alkyl halide, but like one that can undergo I shouldn't say any old one, ones that can undergo an SN2 substitution reaction. And so you get your SN2 reaction here, that provides you that red bond, and you get an irreversible step here. 83% happens to be the yield here, but the yields are very good always. And notice that once you form the carbon-carbon bond, there's no going back. And the reason there's no going back is because to go back, you have to generate a carbanion. And since that is not going to happen, you end up getting irreversibly this alkylation. Now, if I hydrolyze the esters, I end up with this diacid, and then if I heat it, you really remember that you can do a decarboxylation reaction, right? Because any kind of carboxylic acid that has a beta carbonyl undergoes facile decarboxylation through that cyclic mechanism that we saw way back then. So in net, what you've done here is you've taken acetic acid and you've alkylated it, right? I mean, that's what this looks like. So if you look at the final product, and I look at the red bond that I made, it just looks as if I took acetic acid and alkylated it. No. So you look at this and say, well, you know, what's the big deal? I mean, why didn't I just, instead of starting with malonic acid, why didn't I just start with acetic acid, form the enolate, trap it with the alkyl halide, and then I don't even have to do the decarboxylation? What's wrong with that? The answer to that is there's really nothing wrong with that. It's just that it's not as easy to do. That we're going to see that. In order to deprotonate the acetic acid, you have to use a really strong base, and you have to do it under conditions that exclude, you know, any kind of proton source. Whereas here, you can do this with ethoxide and ethanol. You can actually be sloppy, and this reaction will work. And so the malonic ester synthesis is much easier to perform, and critically, it's easier to scale up because you don't have to use these very strong bases, as we're going to see. So this is a useful thing to know how to do. Now, I've shown the malonic ester synthesis applied to the generation of this compound. I can draw this out maybe a little differently for you. So if I look at this compound, I can draw this out as like so. Okay, that's the same compound, right? If I just look at that and I look at the same compound. So that's, you know, if I want, so what I think about you know, if I'm looking at this, somebody gives you this compound, says, make, you know, how are you going to make it? I look at this bond for this connection because I can form an enolate here. Now, I can form the enolate and think that the enolate here is, and I'm going to put this in quotations, and you'll see why. I can think of this enolate reacting with the alkyl halide, or I can think of this enolate reacting with the alkyl halide. And the malonate is a little bit easier to do. Now, this is not going to work as shown, because of course I have an acidic proton. There's no way to form that enolate on the acid. Why? Well, because this is the proton that will be lost first. So now let's ask a question. Let's talk about not making this compound, but making this one. So let's just say that somebody, I'll redraw the structure, says, well, you know, I want you to make this carboxylic acid for me. How do we get started on that? I mean, what's my starting material? Well, as usual, the bonds that you can disconnect are the ones that are alpha to the carbonyl. Why is that? Well, because those are the bonds that you can make by alkylating an enolate. Remember that the carbon atom that's alpha to the carbonyl is nucleophilic. And so if I am able to form that nucleophile, then the two electrophiles that I need to use here are, in one case, a 1-carbon electrophile, that would be methyl iodide. In the other case, a 4-carbon electrophile, that would be, say, butyl bromide or butyl iodide. So the way you make this is as follows. You work backwards, always. And so you think that, well, okay, so the way I got to here was from this dicarboxylic acid by doing what? By doing a decarboxylation. Because I know that malonic acid can be decarboxylated because it has a beta carbonyl. And then I know that I can form that malonic acid by hydrolysis of the malonic ester. And then I can disconnect this one step at a time. I can say that, well, I can treat the methyl malonate anion with butyl bromide. So anion displaces bromide. This can be made by deprotonation and alkylation of malonate and iodomethane. Okay, so any kind of acetic acid, substituted acetic acid, can be prepared very easily using this malonic ester synthesis. And it's, I mean, there's nothing tricky about it. It's just, you know, enolate alkylation after enolate alkylation with a decarboxylation at the end. And so the reason this is useful is because making this kind of anion or that kind of anion turns out to be really straightforward and scalable. And, but it's not the only way to proceed, as I indicated to you. So now let's take a look at the other way to do it. So you say that, well, you know, why do I want to go to this much trouble? Why don't I just take, you know, acetic acid or some acid and do the deprotonation directly. And that way I end up doing less work. Well, it works. There's nothing wrong with it. But look, I need to use fairly specialized conditions. First of all, this is a very common base. It's the isopropyl cyclohexyl amide. Very strong, negatively charged nitrogen here pulls off the red proton and forms this ester enolate quantitatively. Now notice the conditions. This is done at minus 78 degrees. It's done at dry ice temperature. It's done in THF with exclusion of moisture, air, and everything else. And then you can trap this enolate with iodomethane in the normal SN2 reaction, and you end up alkylating here in very good yield. Nothing wrong with this. There are some things to be careful about. Now, this is either the disopropyl, but more typically for esters, you use either this one or the dicyclohexylamide. Now, the base is really hindered. And the reason you need to use a hindered base is because you don't want it to act as a nucleophile. If I used amide, lithium NH2, or even dimethylamide, lithium N-methyl-2, that N-methyl-2 minus is much smaller than the amide that I use. That can act as a nucleophile. And what it will do is it will convert this ester into an amide. In other words, this nitrogen is too big to reach in there and form a tetrahedral intermediate. I mean, it's not too big, but the deprotonation takes place much faster. And hydrogen is small, and so the approach to hydrogen is not inhibited as much as the approach to this carbon atom. And so this acts as a base, very strong base, but acts as a very poor nucleophile. And so that's why you want steric bulk here. You preserve the basicity because in all cases you have a negatively charged nitrogen atom, but by bulking up the groups, by having them either as disopropyls or dicyclohexyls or something like that, you end up with a poor nucleophile. And that's what needs to happen to avoid forming the amide. So, although the base that we used is very hindered, its approach to the small hydrogen is not significantly slowed down, and the proton removal is still fast at minus 78. Now, the one thing you might worry about with this approach, something that you don't need to worry about with the malonate, is that, well, okay, so we form the ester enolate at low temperature. We form it, you know, fairly easily. What's to prevent the ester enolate from just doing a Claisen reaction? Well, in this case, you don't need to worry about the Claisen because why? Well, because it's the ester is disubstituted, and the Claisen can't be driven to completion by forming an enolate. So in this is maybe a loaded case. But in general, you don't need to worry about the Claisen reaction because you can form this enolate quickly. Okay, so in other words, if all of the esters very quickly converted to enolate, then there's no ester enolate to react, there's no ester to react with enolate because it's all enolate. The only time you have to worry about the Claisen taking place when you have ester enolate and ester together. Those can react. But in this case, you can do that deprotonation quickly at minus 78, and then you never really have to worry about a Claisen reaction. So this works really well. I mean, there's nothing wrong with doing the deprotonation of the ester to form the enolate under these conditions. It's just that the malonate, the malonic ester synthesis, is just easier to do. And so you have multiple ways of getting to the same product. This is just what I said about not getting the Claisen reaction. Now, there's a bit of a confusion here that I want to, I want to help you avoid, and that is, it's nomenclature again, which is always a little bit screwy, but when we say amid, okay, when we say amid, what I instinctively think of is something like this, right? And that's an amid. The problem now is that we're using amid to mean two different things. Of course we mean this, but we also mean compounds like this with a negatively charged nitrogen. So they're both called amids. How do you tell the difference? Well, context will reveal the difference. But LDA, remember, is lithium diisopropyl amide. And it doesn't have a carbonyl. This is lithium cyclohexyl isopropyl amide, and this is lithium tetramethylpiperidine. You don't need to remember these acronyms, but you do need to kind of pay attention to the bulk. This is in terms of increasing bulk. This is an extremely hindered base. So these are all prepared from N-butyllithium, typically. N-butyllithium is something you can buy. It comes as usually a hexane solution. You can buy it at high concentration, actually. The more concentrated, the cheaper it is per mole, but also the more hazardous to use. So typically there's a compromise. The stuff you buy is about 2 molar. And so you take the NH compound, you treat it with this very strong base, and so the negatively charged carbon pulls off a proton from the nitrogen. You end up with LDA. The byproduct here, you notice, is butane, N-butane gas. So there's really no byproduct to see. That evaporates away. You never see it. So it's an easy way to make these bases. They're not hard to make at all. Okay, so we talked about the malonic ester synthesis. We talked about synthesis using amide bases. And now there's another synthesis that is almost the same as the malonic ester. It's called the acetoacetic ester synthesis. It's essentially the same. This is ethyl acetoacetate. That's the Claisen product you get from ethyl acetate. You already know that the methylene group that's flanked by the 2 carbonyls is acidic, highly acidic, so I can pull one of those protons off easily and form this enolate. This enolate can be used as a nucleophile in an SN2 reaction to undergo alkylation in high yield. And then I can do exactly the same thing that I did before. I can hydrolyze the ester and do a decarboxylation. So it looks pretty much identical to what I showed for the malonic ester synthesis, except the final product now is not a carboxylic acid, but in this case a methyl ketone. And so this is another way to alkylate acetone, if you will. I mean, the other way to think about this is I start with acetone, I form the enolate, and then I trap that enolate with butyl bromide. So it looks as if that's what I did. Now, why would the direct alkylation through the enolate of acetone be problematic? Well, acetone is a heck of a lot more reactive than ethyl acetate. And so forming the acetone enolate is sometimes tricky because there you do get alkyl reactions. And so this has an advantage over the direct deprotonation of acetone. Now, just as we saw with the malonic ester synthesis, you can also do dialkylation reactions. In other words, you alkylate it once, you alkylate it the second time using the same or different electrophile, then you hydrolyze the ester, then you decarboxylate, and now you have a alpha disubstituted ketone. So you think of acetone being alkylated with methyl and butyl here. So it's the same, it's essentially the same. If I had, instead of a methyl group, if I have an O-ethyl here, then it's exactly the same as what you saw before, nothing different. So this is useful. This is actually a useful thing to be able to do in the lab. And one more thing. I mean, I've indicated that this works for ethyl acetoacetate, but you should recognize that I could have had this as the starting material, okay, where this is any R group you want, and I will still only alkylate here because this is the acidic methylene, not that one. And so if I carry this through the same synthesis that you saw before, at the end of it, I'll have a species like this, right? I do a dialkylation. So alkylate it with R1 halide, alkylate it with R2 halide, hydrolyze decarboxylate, I'll end up with this as my substructure. So I don't need to end up with a methyl group here. I mean, it could have been anything else. Okay. So, at this point, you may be thinking that, boy, you know, there's a lot to remember here, or it looks, you know, it looks complicated. I'm going to repeat myself. What you want to focus on are the mechanisms, okay? Once you understand the mechanisms, deprotonation, alkylation, decarboxylation, and so on, this stuff is all the same. There's really nothing different here. We haven't talked about anything that's, you know, radically different. Maybe little tweaks here and there, but overall, it's the same stuff. Now, we're going to switch gears just a little bit. We've talked about this chemistry also, but now we're going to talk about it in maybe a little bit more detail. These are conjugate addition reactions. And these are also known as 1,4 addition reactions or Michael reactions, named after the British chemist who described them first. So let's take a look at it. You know, and I'm going to use Michael reactions or conjugate additions. I'm going to use these terms interchangeably, so please don't be confused. So let's take a look at one of these Michael reactions and see how it works. So I'm going to start with an alpha-beta unsaturated ketone, this one here. And I'm going to take hydrogen cyanide and cyanide. And what I get out of this is this beta cyanoketone in essentially 100% yield. So the cyanide, which is what? Cyanide is a nucleophile, right? It's always a nucleophile. That nucleophile reacted with a beta, with a beta carbon atom. Now, we're going to look at the mechanism in a moment. But it's very important to recognize that this carbonyl group is absolutely essential, okay? If I don't have that carbonyl group, I'm not going to get that Michael reaction. Because if I start with this compound, stilbene, and I treat it under identical conditions, I'm not going to see any reaction at all. Okay, so this reaction proceeds precisely because I have an alpha-beta unsaturated carbonyl compound. Why is that? Well, you look at the mechanism. And if I look at the starting material, recall that the starting material has these 3 resonance structures that I've shown you in the past. And so the beta carbon atom for an alpha-beta unsaturated ketone, an alpha-beta unsaturated ester, an alpha-beta unsaturated anything that has an electron withdrawing group attached to the vinyl carbon. Remember that. Any electron withdrawing group attached to the vinyl carbon is going to give me Michael or conjugate addition. Why is that? Well, because I can always write these resonance structures where I have a partial positive charge at the beta carbon atom. I have a partial positive charge at the beta carbon atom. Cyanide can form a bond like so. That gives me the enolate. The enolate gets protonated by cyanide, regenerating cyanide. These are the resonance structures. Regenerating cyanide as the catalyst and the ketone. So this enolate is resonance stabilized. Now, the reason that the reaction works for the ketone and does not work for stilbene is exactly here. That the intermediate that you form is resonance stabilized. Whereas, if I started with stilbene, this is, well, okay, you say this is resonance stabilized too, because the negative charge is benzylic. Yeah, that's true, but it's a much stronger base, right? Because the negative charge never ends up on an oxygen atom. And so the reason that this chemistry works is because of the stability of this intermediate. The stability of the intermediate through Hammond's postulate suggests that the activation barrier to get there is low, and so on and so forth. Okay, so this doesn't look all that different, but there is a question that you should always ask.
Compared to what?
Huh?
Compared to what? Compared to what?
Well, okay, compared to what? No, it's not the compared to what question. It's here. The cyanide adds to the beta carbon atom, but look, I have another resonance structure, don't I? And so the question that you should ask is, okay, so it gives you the beta adduct, but why didn't I form a cyanohydrin? Don't you remember cyanohydrins? We talked about cyanohydrins, right? So the question now that we have is, well, seems to be kind of a duality here, right? Because the cyanide, it could have formed a cyanohydrin, but it didn't. It gives you the conjugate addition, it gives you 1,4 adduct. And the reason for that is maybe not too hard to see. Here's how you figure this out. Look, let's go back. Let's take a look here. So we have two products possible, right? Let's just show the reaction. So I can get the 1,4 product. That's the conjugate addition, and that will give me what we just saw. We'll get that. Or I could have gotten the 1,2 addition. That would have given me the cyanohydrin. Okay. Now it turns out that this is what you see, and that's what you don't see. The reason being that that the CO bond is stronger than the CC bond. Okay, so you are getting a thermodynamic product here. So in this case, this is going to be the thermal product. And in this case, this is actually the kinetic product. And so we're going to come back to that. But remember, you heard it here first, okay? So the reason that these reactions give you conjugate addition is because we are getting the thermodynamic product under these conditions. We're gonna take a look at this again in a bit. Now, I said that you'll get this conjugate addition business, this micro addition, whenever you have a pi bond, a C double bond C, where you have an electron withdrawing group attached to one end. And so let's take a look at some of these and see if we can see, so we can recognize these. So we saw ketones. Aldehydes will do the same chemistry. Esters will do the same chemistry. Vinyl nitros are excellent Michael adducts. So you can do Michael acceptors. So you can do conjugate addition to that carbon atom very, very easily because it's a powerful electron withdrawing group. Nitriles also sulfones, and there are others, but these are the main ones that you'll see. So all of these kinds of alpha-beta unsaturated compounds will participate in this kind of chemistry. So the way to think about it is this. The way you think about it is don't memorize, say, oh, keep out. The way you think about it is that I have a double bond and I have a W group. What's a W group? That's an electron withdrawing group on it. Okay? So if I have a W group attached to that pi bond, now what is that telling me about the pi bond? Well, it's telling you that that pi bond is polarized and that I'll have a partial positive charge right there. And if I have that partial positive charge, then negatively charged nucleophiles can react with it. Okay? And I can delocalize the electron pair into the W group, which is what happens in each and every one of these cases. Okay, so now the nucleophile that we looked at was cyanide, and nothing wrong with that. That's a good nucleophile. It's carbon nucleophile. It's not the only one. And the nucleophiles that you can use for these conjugate additions are indeed highly diverse. There are lots and lots and lots of ones that will work. They will work either heteroatomic ones or carbon nucleophiles. And so we'll take a look at a few of these. So thiols work really, really well. And so you can imagine here pulling off that proton using methoxide. Now you have a thiolate, excellent nucleophile, electrophilic carbon. You end up forming this bond here, essentially 100%. Amides. not bad nucleophiles in this case, and so that you can get under, if you just use the amine, you can get the beta amino ketone in good, in very good yield. So in both cases, you notice that you'll see. So the way you recognize that you had a Michael reaction, or 1,4 addition, is that you have an electron withdrawing group here, and here you have something that was a nucleophile. And so that's the substructure you look for. When you see that, you think, oh, this must have come from a Michael addition of like so. And so this is the substructure you look for. You look for the alpha beta carbon atom as the what used to be the nucleophile. So coming over here, that's the alpha carbon, that's the beta carbon, that was the nucleophile. Alpha carbon, beta carbon, that was the nucleophile. With quinones, there's kind of an added driving force, and that is the product is aromatic. So quinones are really good Michael acceptors. They will undergo nucleophilic addition very quickly, and of course irreversibly, because you form an aromatic ring. How does the aromatic ring form? Well, it just forms from a ketoenol tautomerism. So you can think of the thiol adding, that will give you this intermediate. That doesn't stick around, because once that thing enolizes, you've got the aromatic ring, and then the process is completely irreversible. And now all of these conditions were either basic or neutral, okay? And it's not the only way to do a conjugate addition. But you can perform these reactions under acidic conditions too. So acid catalyzed Michael additions or conjugate additions are also known. And I've indicated two here using just hydrogen halide. And so HBr, HCl, HI, those can all do exactly the same chemistry. Now, in this case, of course, the mechanism is a little bit different because it's done under conditions of strong acid. When you have a carbonyl group and you have strong acid, the first thing that's going to happen is what? The first thing that's going to happen is going to be activation of the carbonyl. So you're going to get the activated carbonyl first, as shown. The activated carbonyl can certainly add bromide as seen, but this is unstable, and this is reversible. So instead, you go down the green pathway, the conjugate addition, that gives you an enol, this gives you something fairly stable. And so here we are again with this business of, why do you get 1,2 addition in some cases and 1,4 addition in another? And so the site of highest reactivity actually is the carbonyl and not the beta carbon atom. Okay? So the greatest reactivity is here, not there. So then the question is, well, how come we don't always get 1,2 addition and we get 1,4 addition? That's the business of kinetic versus thermodynamic control that I indicated. So there's another, we're going to see this now again in a little bit more detail. Remember that bromide is a very weak base, okay? And remember also that thiolate is a fairly weak base. Thiol is a weak base. The amine, not the amide, the amine is a weak base as well. Not a very strong base. So all of these, and cyanide is not a particularly strong base. So in all of these cases, we've seen conjugate addition of nucleophiles that are fairly weakly basic, not strongly basic. So that means that we can make actually a good generalization. So here we are now. How do we tell that we're going to get 1,4 and not 1,2 addition, or vice versa? So we have to have a way of telling, when we look at substrate, reagent, what's going to happen? Is it going to give Michael addition, 1,4 addition, or am I going to get or am I going to get 1,2 addition of carbonyl? And so with weakly basic nucleophiles, you always get 1,4. With strongly basic nucleophiles, you always get 1,2. And so it turns out that the kinetic product is the reaction at the site of highest reactivity, which is the 1,2. That's less stable, however, because this is a weaker bond than the ketone. And the slower process that takes place with weakly basic nucleophiles gives you the more stable product. So you end up with weakly basic products, 1,4 addition, thermodynamic control, strongly basic nucleophiles, 1,2 addition, kinetic control. So fast kinetic control, slow thermodynamic control. And so, yeah, the reason that the 1,2 addition is faster is just because the resonance structure that places a partial positive charge on the carbonyl carbon is more important than the one that places a partial positive charge on the beta carbon atom. So in other words, let's remember what we said about resonance structures. So if I have this ketone, I can draw 2 resonance structures. I can draw this one, and I can draw this is more important than that one. Why? Remember we talked about rules to try to determine which resonance structures are going to be useful. When I say more important, what that means is that it contributes to a greater degree to the overall structure. Remember that the structure of that alpha beta unsaturated ketone is not really adequately described by any one of these structures. It's kind of a weighted average, but I give more weight to this and less weight to that. Why is that? Yeah, because this has a higher, a larger separation of charge. And so the charges aren't separated by as much. Here's 1 bond, here's 3 bonds. And that's why this is more important. Now, so you knew that from first principles. And so the 1,2 addition being faster than 1,4 kind of makes sense because the most of the positive charge is on the carbonyl carbon after all. Makes sense. So, and then I already mentioned this, right? The reason the 1,4 adducts are lower in energy than the 1,2 is because the CC double bond is weaker than the CO double bond. And so the 1,4 adducts preserve the CO double bond, the lower in energy than the ones where you get 1,2. And so this is a very good, very useful generalization. It allows you to make good predictions. So the preferences, as I mentioned just a little while ago, you can see our example of kinetic versus thermodynamic control. So with a weakly basic nucleophile like cyanide, you can do this, but you form it reversibly. So the cyanohydrin is surely formed in this reaction, but it's a reversible reaction. It's formed fast, reversibly, and then at some point you get the Michael addition, the 1,4 addition, and that gives you the stable product, and that's what happens. So you get this reversible equilibrium, but eventually it all ends up here because this is more stable. Now, if I have a strongly basic nucleophile like hydride, you always reduce the ketone or the carbonyl group selectively. And so this is an example of kinetic control. And why is that? Well, because H- is a strong base. Grignard is another good example. So if I treat these kinds of compounds with, say, methyl lithium, that you always get the 1,2 adduct, okay? Because methyl- is a very strong base. Now, that begs the question. Let's say that I don't want the alcohol. Let's just say that, I don't want to do it that way. I have this ketone, and what I really want is I want to add R prime minus. So this is a carbon nucleophile, but I want that to add 1,4. Isn't there a way to get this carbon-carbon bond selectively. And then after protonation and workup, I would end up with a ketone. So this is the bond I'm making. Isn't there a way to do that? Because that would be very useful, wouldn't it? Because it's another way to form carbon-carbon bonds. Now, we saw a way to form a very special case of carbon-carbon bonds. We saw cyanide as a nucleophile. Sure, cyanide's great, but it's not the only carbon nucleophile we have, and certainly not the most useful one. Isn't there a more general way to do this? And the answer is, yeah, there's lots of ways, actually. And so one way is to do the Michael addition using malonate. So you saw that malonate, just earlier this morning, the anion can be trapped with alkyl halides. But alkyl halides are not the only electrophiles. Alpha beta unsaturated ketones are also electrophiles. And so malonate can react, so this pulls off the proton, can react at that carbon atom to give you a new ketone, or ketoester if you will, with formation of this red bond. And this process takes place in good yield. Okay, so we'll stop here. We'll pick up on Wednesday, and we'll continue our discussion of